Thank you very much, Boris, and hi to everyone. Thank you for ERM for hosting us in this webinar. You are here today with us in our home, not far from Tel Aviv in Israel. This is where our headquarters is located, and this is where our production site is. And what we're going to do today is a short webinar. We're going to present a few slides just to give everybody the proper introduction. And then we will move on very quickly to showing you the actual machine, which is right behind me here. This is the big one, the dominant machine. We will show you how exactly it works. We will go with the camera inside the machine and show you the different parts and the different stations so everyone can see what it's all about. So just a few words regarding Triton. Okay, so basically the MoldJet technology, we call that the MoldJet because actually we are jetting the mold and not the actual part. We use a cast material for producing a part. This is a powder-free technology, unlike many other AM technologies, metal AM technologies. The cast material is applied into the mold, which, as I said, we are printing. And this is the way, layer by layer, we are building the part. This is a technology that is based on sintering the green part. So the system produces green parts, what is called the green part. It's not the final part. Those parts have to go through a sintering phase, which is a standard in many technologies, in many industries, such as MIM, which includes demolding, debinding, and sintering. Those are the post steps that we have to go through in order to get the final part. Now I want to walk you through the main 4 phases that actually happen inside the machine. So if you can see me, it all starts with this table or tray, what we call tray, which is mounted onto the machine. This is a metal, very heavy metal and robust tray. On that, we are placing or molding an initial layer of the mold material. This is the mold material, which you see in the clips and in the presentations. The typical color is orange, but sometimes it's a different color. Anyway, we place it, we glue it actually to the table, and on this surface, on this initial surface, this is where the machine starts printing. Okay, and then, as I said, it's a layer-wise process, and we have 4 main stages. So the trays are actually placed on a kind of a revolving table. We have 6 of them that work simultaneously, and then the phases that are happening on the machine are as follows. The first phase is the mold jetting, or the creating the mold. So this is the picture that you see, number 1. We have printing heads going, traveling over the surface and jetting the mold material layer by layer. So I'm going to walk you through the process for each one of those layers. So the first step, as I said, is jetting the mold so that we create the actual pattern or the contour of the part. The second phase, under number 2, under picture number 2, is we are using, as I said, we are using cast material, which actually has the properties of a paste. It is powderless. It is not anything that you have to be concerned about when you work with. It comes inside those tubes, those plastic tubes. It's actually the mechanical properties are very similar to any other paste that you can think of. It comes inside those tubes. Those tubes are placed inside the machine. And then this tube is the feedstock actually of the mold material, of the cast material. So the cast material, under picture number 2, you can see we call it a die slot. It's actually a very long, narrow slot which travels over the tray, over the surface, and deposits the cast material. After it does so, the layer goes into a heating phase, which is the function of it is drying actually the cast material. And then the last station is an inspection station where we have a special artificial intelligence algorithm with a very sophisticated camera that takes the pictures or scans the surface layer by layer. We have a log and we have a very sophisticated algorithm that helps us understand whether the layer is correct or incorrect. So if we find defects, we have a chance to correct the part as it is being printed. So actually, theoretically, we can get 100% yield because we find the defect in the process, and we can do go one step back. So in case we have a defective layer, which is not, it doesn't happen very often, but when we have that, when it happens, first we have an indication because we have a very innovative and sophisticated algorithm for that. And secondly, we can undo, we call it undo the layer. So we can just cut the layer, remove it, and go back one step and keep on producing the part. Now this, can you move on one slide? Okay, so that's what I just described up until now was the process that happens on the machine. In the end, we have this, as I said, this tray has the mold layer on it, and it keeps building up. It depends on what is the size of the part that we're producing. In the end, we have a tray. It looks like a very big wafer, okay? And we just unload it from the machine and move on to the post-processing steps, which are not happening on the machine. And I will describe them to you now. So the first step is called the demolding. Demolding is actually removing the mold material and being able to hold the parts in your hand. So we need the mold material to be removed. And this is what you see on the left side of the slide, picture number 5. You can see how by a thermal process, as well as the solvent that we use, we just remove the mold material. So the orange material that you see is being removed, and we are left with the green part, only the parts. Those parts have to go through 2 more steps in order to be ready to use. The first step is debinding. So the paste material that we use has a material called a binder. So the binder is the material that keeps the particles of the metal together to keep them in the geometry that we gave them during the printing process. This binder is not part of the final part. We need to remove it. This is called the debinding process. It happens in a furnace at certain temperatures, and this is the process. It's actually the same like baking the part. And the last step is the sintering step, which is actually a very standard process in several industries. It is a very old. It is known for many years. We don't have any innovation in that sense. So it's a sinter-based process. And in our case, we do the debinding step and the sintering step in the same process. So we have one furnace for both stages, and this is how it works. In the end, when the sintering process is finished, we open the furnace and we have the final parts. Final parts can be used as they are. It depends on the function. And of course, as always with the metal processing, it can go through any other standard post-processing step that you can think of, heat, thermal treatment, or whatever treatment that it has to go through. So this is what we have to say about the system itself. We just wanted to show you one example just to get you some relevant information. We have a part, we call it a T adapter. You can see it here in my hand and also on the screen in the slide. This part is analyzing, where we tried producing it and we analyzed how much is it going to be the time to create it, to produce it, and the cost. So on the screen you can see the results. Some of you might be able to see that actually the cost is relatively low. It depends on what was the traditional way by which this part was manufactured in the past. It's an aerospace part, and we have many more examples such as this one, but just I wanted to everyone to have this kind of quick reference to what exactly is coming out of the machine and what is the actual cost and time that it takes to produce it. So now we're going to move on to show you the machine without further ado. I'm going to present to you Roy. Roy is an application engineer here in Triton, and he will show you the machine. He will go around the machine and into the machine. And as we said, in the end, you can ask questions. And we're also going to show you a few more parts that we brought as samples, just to see the product that comes out of the system. Okay.
Thank you so much.
All right, hello everybody. As Amnon mentioned, my name is Roy. I'm an application engineer here at Triton Technologies. What I'm going to be doing is walking you around the dominant, showing you the user interface and all of the stations that Amnon previously mentioned. So first, as we have over here, this is our user interface. As you can see, I can look at every single station, what is happening at each station, and controls. Here you have your inspection. As Amnon mentioned, the camera system. Over here, you have the jobs that are currently printing. This is the information on the mold. As you can see, the temperatures are not too high. We have our material station, pre-drawing, and drying. As Amnon mentioned, our system is a powderless system, which allows us to be in an open environment in a regular room working around it. As you can see, the machine is currently printing, and I can walk inside and not worry about wearing any protective equipment. What you can see right now is our 4 print heads printing the mold. Right over there. The station moves from the mold station to the MDS, where we have an initial cutting of the layer. And then we go ahead and supply the tray with our paste material. I'll just show you guys how it looks once the tray goes down. And there it is, that's a new layer. Next, what we will do is we will proceed to the pre-drying station, which is right over here. What we did on the dominant is we went ahead and split the drying stations into 2 to go ahead and shorten our manufacturing time and increase our throughput. As you can see over here, we have 1 heater inside, right over here, and our second heater here. And this is also the station for where we insert and remove our trays. Let's see. The next station that we have is our vacuuming station, which is right over here. The tray will come into position, the vacuum will go down, and this is actually our curing phase. So what you have first is drying, secondly, you have curing. And what that does is it removes all of the leftover residue and hardening the grain parts. After the curing phase, we go ahead and move into the final stage, which is right over there, right over here. This is our inspection system, where right up there you have our camera that takes a picture of the tray, and where our inspection AI system starts to work. Second, now what I want to do as well is show you a few examples of our printed parts with various materials. But first, I'll go ahead and introduce you to our second product that we currently have in work, which is our DIM. As you can see, it is much smaller than the dominant. It is also used for a upscale production, but the major difference between the 2 machines is that our trays are substantially smaller. This is for a company that would be interested in producing smaller components. As you can see, we have 4 stations rather than 6, but this is our second product that we're currently having work. Now, what we have over here is a table with some printed parts of various materials. What I do want to show everyone, which is very interesting right over here, is a titanium part that we managed to print. Titanium, it is sintered. And what we went ahead and achieved was a 97% density on this part over here. You also have an example of a T-valve that had post-processed threads completed to it, right over there. So we're showing that our parts are very robust. This is actually 15.5. They can be sintered and then post-processed on conventional CNCs as well. You have over here a green part of a drill. What's interesting about this drill is that it has internal channels right over there. If you can see them. And the sintered sample of the same exact drill. And here's a size comparison of side by side. We have a shrinkage rate of roughly 15%. And if we go ahead and cut the drill in half, this is the internal features of the drill. So you can see the channels going through the drill and coming out to the other side. Here we have a same exact drill, but much, much smaller, same sample. Additionally, we have parts over here that can show our ability to print mesh internal structures. You see, so you can remove mass from your products, from your parts. We have parts over here that shows you size comparison, going from large to medium to small to show you our ability. We have the ability to print internal features, internal curvature features that are open and allow for fluid transfer. And lastly, some internal geometry that is able to be done on conventional CNC, but takes an substantial amount of time. And we show the ability that we can print these parts as well and use them for many industries. Another sample of open features, internal features that curve, are these channels right over here. They follow this S pattern and come out the other side.
One question from my side. What about the behavior regarding supports with your process?
Okay. So
it's
yes,
very interesting regarding internal geometries.
As he mentioned, we're also able to print supports, which is right over here. The titanium part was printed with a support under it. And what this is a sintering base. And so during the sintering process, to make sure that to minimize the possibilities of our geometries being affected by the high temperatures, what we do is we print it on a sintering base for certain geometries, and they both have the same shrinkage rate. So they just shrink together. We spray these with a zirconia spray that allows them not to stick. And then what we get is a part that we can use this and then remove this after.
Okay. Thank you so much.
Another sample is right over here as well. We have this, and which is printed on this base right over here. It fits right inside.
Okay.
So that was a brief overview of the dominant. Boris, if there are any questions from anybody, feel free to open them up. I do want to show one thing, just quickly. As Amnon mentioned, this is our where our material is loaded, how this is loaded into the machine. Where we load it is very simple. We have this entrance right over here. And what you see over here is you have our rotating, where the tube is rotating to make sure that the material does not set. Right over here. Okay.
Feel free, n'hésitez pas à poser vos questions au passage, en français ou en anglais, il n'y a aucun problème. On se charge de la traduction au fur et à mesure du webinaire si certains ou certaines d'entre vous ont des questions. Yes, you can go.
Okay. This is actually, that's it from us. If there are any questions, I'd be happy to answer them, whether it's regarding the process, whether it's regarding the machine, the stations, the components that we have in front of you.
Sorry, there was some noise at the same time.
Yeah, it's the machine.
Yes.
What I was saying is that's it from us. If there are any questions that anyone would like to ask regarding the process regarding the parts that we have out in front of you, the machine, the stations, I'd be happy to answer them.
Okay.
Oh,
Donc,
yeah, Ramon just reminded me, just so that you guys know, we do have a variety of stainless steels that we can print out of, manufacture out of. We have 17.4, 15.5, 316L. We have Inconel 718. We are currently, as you saw, working with a titanium. We also have copper that we're currently working with. We have H13 tool steel. We have alumina right over there.
yes.
It's actually interesting. We started printing teeth. So we have a lot of teeth running around the factory right about now.
Okay.
And yeah, we'd like to open it up
Yes.
for questions.
Some questions incoming. The first one is from Thierry Poirier. Can we, during manufacturing, during printouts, can we replace the cartridge of material if this is out of material? Can we do it
Yes,
during the process?
Yes, of course. So basically what would happen, just quickly, I just want to show you a copper part that we went ahead and printed as well. Sintered coppered part.
Perfect.
So yes, to answer your question, the change of material is very simple and easy. What will happen is you will get a notification in the material station saying that your tube is out of material. As you see right over here, this is how much material I have left. I have 58% left in my tube. But what I'm gonna go ahead and do is pause the job for you. What you do is you open it over here. The machine goes into a brief pause, lets you know, hey, you're out of material. You cannot proceed. The tube will stop rotating. Yeah. Just 1 second, let it get to its stop position in 3 seconds.
Something in French that just while you are waiting. Donc pour tout le monde, du coup, un des gros avantages, je pense que tout le monde l'a compris, c'est que ce système est complètement exempt de poudre ou voilà, ne nécessite pas forcément d'EPI spécifiques vraiment pour accéder à l'intérieur de la machine. Yes, you can go.
So now that the tube has stopped rotating, I have the lever right over here, down there. I open this lever and I remove my tube from here and replace it. The process takes no more than 2 minutes to replace the tube. So yes, you can easily replace the cartridge. Once it's replaced, you come back here, you let the machine know that you inserted a cartridge, it's inserting, the cartridge starts to rotate again, and I hit play.
Perfect. Yeah. Do we have some kind of, as users, if we are not in front of the machine during printing, do we have some notification?
So what happens is, as the machine rotates, it sends up. There's a siren inside to warn the user, first of all, that the table is about to rotate, right? And a red light flashes. So there's a visual and an audio warning. And if you're not around the machine, and the machine stops printing because the cartridge is out, what will happen is the machine will stop moving. So from far, you'll see that the red light isn't blinking anymore, and that there's no audio sound playing that the station has rotated because it's waiting for you to change the cartridge.
Ok, perfect. Est-ce que, Monsieur Poirier, nous avons bien répondu à votre question? N'hésitez pas à rajouter dans les questions directement si c'est très bien. Bon, super. One other question from Mr. Savini. Mr. Savini, you can also download datasheets of every machine from our proper websites or directly on Triton website. Can you tell Roe about maximum dimensions of parts we can do with both machines?
Yes. Okay. So currently our tray, right over here, we have a brochure. So as you see, the build volume is for the dominant right, is right over here. So you have 400 in the length by 240 by 120 millimeters high. You know, just recently we started experimenting with massive objects, and we went ahead and were able to print a part that weighed 4.8 kilograms in the green state, which took up half of the tray. We also had 2 airfoils that we managed to print from edge to edge. So right now we're experimenting and seeing the viability of printing a large scale product that is the entirety of the tray. For the DIM, we have it right over here. The DIM is a smaller tray. You have 220 by 120 by 90 millimeters, which you can also print in the full capacity of this tray as well.
Okay, thank you so much. Monsieur Savigny, on vous enverra. N'hésitez pas à rajouter vos coordonnées si ce n'est pas déjà fait dans l'onglet Q&A pour qu'on puisse vous envoyer les datasheets des 2 machines après le webinaire. Roé, one question regarding Mr. Savigny, last question. Can we do bigger parts than the tray in some other process, kind of process? Like?
So there is something that we are working on currently, which is called sinter bonding, where you would print the two. First of all, to extend past the build plate itself, you can't, because our print heads, you know, we're printing the mold onto this material. And if you print off of the tray, you'd be printing into the air. So essentially, you know, you can't, and also we're restricted mechanically within these bounds. But what you can do, which is something that we started experimenting with, is you would print 2 halves. You would combine them, put them one on top of the other, and you would sinter them
like that.
in this fashion, like this, and they would bond and stick in the sintering phase. That's something that we started working with. We have a few trials, and it's so far it's been working.
Okay.
Yeah, it helps reduce cost if your part is high in the z-axis, and it's very common to be, if I'm not mistaken.
Donc pour répondre, un complément de réponse à la question de Monsieur Savigny, c'est qu'il est possible aussi d'imprimer des pièces dans le plan de symétrie et au moment du passage pour la partie sintering à la fin du process, l'idée c'est de combiner les 2 moitiés de pièces pour pouvoir les friter en même temps. Donc ça c'est un mode de fabrication qui peut être très intéressant pour faire des géométries plus complexes internes et voire faire 2 moitiés de pièces pour pouvoir faire une plus grosse pièce à la fin. Thank you. One other question from Mr. Poirier. Okay, so the question concerns the artificial intelligence on the camera to help to avoid bad layers. Can you explain a little bit more how the printer does to eliminate the layer?
Of course, yes. Of course. So a little bit more about the AI system. What it does is it takes a picture of your printed layer, and it knows how to compare it to the bitmap. Let me show you what the bitmap looks like. It's right over here. If you look over here, this is a sample of your bitmap, which is white and black pixels. It shows you what's going to be printed. So what it does is it compares your current layer to the bitmap, overlays them one on top of the other, and looks for certain defects. Looks for whether it's blisters, for scratches on parts, looks for overlay or missing infill. And what it does is we've taught the AI system, we've taught it how to see the specific errors and know what to do next. So for example, if I have a blister in a part, which is like a bubble on the surface, I don't want it to go to the printing stage so it doesn't damage my print heads. So it stops the printing, it brings it back to our cutting station. And what it shows you, where it goes to, is our cutting wheel, which is right over here. We have a cutting wheel there. We have a cutting wheel right over here, which rotates and cuts away at the defective layer. So that's how we remove layer. We can cut away a defective layer. And then what we essentially do on the bitmap is go back to a previous layer and reprint it and repeat the process from the beginning. if the AI notices that the defect is repeating itself in a certain area, it throws a warning to the operator and saying, hey, based on the certain error that you have, do these certain checks to mechanically fix or check what the problem is with the part, with the printer. So if it's a scratch, it'll tell you to check the screen, it'll tell you to check the knife. If you have blisters, like I mentioned, it'll tell you to check the heating time to make sure that you're heating more, that you're heating long enough in order to dry the material. So it knows based on the type of defect what procedure is needed to fix it.
Okay, thank you so much for our explanation. It was pretty complete. Est-ce que, du coup, Monsieur Poirier, est-ce que ça répond à votre question? Est-ce que vous avez besoin d'une clarification, traduction? Donc, en gros, pour résumer, le principe même d'avoir une cire et une matière sous forme de pâte permet facilement de pouvoir couper la couche en cours, et l'interface d'un point de vue de l'intelligence artificielle, d'un point de vue des photos, de la prise d'images sur couche par couche, permet d'avertir l'utilisateur sur différents problèmes qui peuvent survenir à l'impression, comme un manque de remplissage, comme trop de matière qui pourrait dépasser de la couche et donc abîmer des têtes d'impression, etc., etc. Et donc, selon le type de défaut constaté, donc la façon d'enlever la couche sera pas forcément toujours la même. Et dans tous les cas, la couche peut être éliminée physiquement pour pouvoir reprendre l'impression à la couche d'avant. Donc, est-ce que ça répond à votre question? N'hésitez pas à le dire, ou si vous avez besoin de clarification, n'hésitez pas. Oui, I have some other questions, so I am computing everyone. So,
okay.
What? Okay. The last question about removing the layer. Does it? Do you have some feedback? Does it affect the mechanical properties of the green parts?
From what it does not. Most some of our parts we purposely remove layers to test that, and so far we haven't seen any defects with our green and sintered parts.
Okay, I think on my side, I think this is the same kind of if we have during sintering after, if you have to put two half parts, this is pretty the same in kind of removing and adding something else. So yes, it should not affect the final result.
It should not affect it also, because what happens is when we remove it, we also in our program go back a step. So you repeat that same layer. There's no way for you to miss a layer that you remove.
Ok, so, donc pas de le fait d'enlever la couche finale, on ne continue pas une fois que la couche est enlevée, on revient en arrière et on réimprime la couche. Mais comme là on est sur l'état de pièce verte, il n'y a pas de manque de fusion ou de manque de matière. La couche est tout simplement reproduite. Donc ce n'est pas censé altérer le résultat final. Ok. One question from Mr. Dacruz, Hutchinson. Hello, Mr. Dacruz. Nice to meet you again. I think the question is regarding different materials. How time does it take to change material, to go from stainless steel to hardened steel, for example?
Of course, very good question. It is a very easy and simple process for us. There is the die slot, the plastic tube. There are a total of 3 or 4 components that are very easily removed from the machine. All you do is take it to your sink. You can rinse it with water, dry it off with compressed air, reload a canister with a new material, and you're good to go. It is very simple, not too complicated. I'll go ahead and show you the components that need to be removed. It is 1, 2, 3, your die slot, and then 4, your tube, which is inside. That is all. Once those are removed, those are the only things that see the paste material Once that is removed, you can load in your new other face, whether it be 17.4, 15.5, 316, and you're good to go.
Okay, so Monsieur Dacruz, est-ce qu'on a répondu à votre question? Mr. Dacruz told us, okay, so I think the explanation, the answer was pretty clear. So, comme vous avez pu le constater, donc passer d'une matière à l'autre, malgré le fait que la machine soit imposante physiquement, avec quelques composants à remplacer, pas de contexte de poudre, pas d'environnement poudre, des composants à changer sont très spécifiques entre les différentes matières, donc on peut passer d'une matière à l'autre plutôt rapidement. Okay, so one other question from I don't know who, anonymous spectator. Do you provide equipment for additional steps, wax removal, sintering, etc.? So I can let you reply, but I have also the reply on that.
Okay, so if you'd like, you can go ahead and take it if you have the reply.
Sorry?
You can go ahead and answer if you have the reply.
Ok, so, donc le ERM Fab Test est le distributeur de l'équipement Triton. Triton est au départ donc manufacturier de la partie fabrication additive, donc tout ce qui est pièces vertes, la machine que vous venez de voir. Comme nous sommes les importateurs de Triton Technologies en France, nous pouvons fournir l'ensemble de l'équipement process jusqu'au four de fritage qui n'est pas forcément qui n'est pas fait par Triton Technologies, mais nous avons la capacité de vous proposer le process entier composé de différentes marques, mais le process entier, donc en passant directement par ERM Fab Test, avec installation, formation, des plans de maintenance, une équipe qui rayonne sur la France entière, qui est capable de répondre rapidement à vos besoins, vos problèmes, y compris toute la partie consommable. J'en profite pour répondre sur la partie consommable et spare parts donc de Triton comme des marques qui permettent de compléter le process. ERM Fab Test est capable de fournir l'ensemble des spare parts et des matières. Okay, one other question from Rémi Siguré. Okay, is alumina as easy as for printing, easily printing as metallic pastes, and do you plan to add other ceramics like
so currently
yes.
Okay, so very good question. Currently our alumina is still in the beta phase. It's not a released product. You know, we want to make sure it's the same process, same components. We don't change anything in the machine. All we want to do is we want to make sure that it's a very robust system before we go ahead and release it. As you can see, I have aluminum parts here, you know, that are printed, that are manufactured. They're already sintered as well. We are currently working on the formulation to make it as robust as possible before we go ahead and release it.
Okay, so thank you so much. Monsieur Siguré, n'hésitez pas à me dire si vous avez des questions complémentaires, si vous souhaitez une explication, ou si au contraire, Roué a bien répondu à votre question. I can add something from my side. This is very important also because we go from machines to machines for all the whole process. And one very good point regarding Triton technology is that green parts are very hard directly after printing. So we can take them in the end, we can take parts in the end, we can transport them, etc., etc. Quelque chose de vraiment important. Donc, le fait de travailler avec une pâte fait que la pièce verte n'est pas fragile en soi. On est déjà sur des pièces qui sont mécaniquement transportables, manipulables à la main, etc., etc. Bah, comme est en train de le faire Roué en ce moment.
Also, if I can, I would just like to add to your answer. Our green parts have been measured to withstand up to 15 megapascals of force, which is fairly high. And also, as you can see, this is a green part over here, right? And I'm dealing with it very violently, you may say. I can hit it in my hand, it's not breaking. So as he said, very robust green parts. Also, just to go back a few steps and ask, to answer a question about two things that were asked previously. First of all, this is another component with internal features. As you can see, this is the inlet, and this is the outlet of this geometry right over here. It's a water heater. Secondly, I'm going to compare this to the size of our tray. That is a centered part. It is a gear. It is fairly heavy. And we managed to center this in one try. And we went ahead and print, this is, we have a few more coming up, but as you can see, very large parts that have been printed.
Donc, quelque chose aussi à comparer aux différents process et aux différentes technologies qui peuvent exister aujourd'hui sur le marché. Généralement, les technologies qui existent sur le marché, on va dire les technologies non poudre, non poudre. Souvent, on ne peut que faire des pièces soit très massives, soit très fines, mais combiner des géométries massives et des pièces lourdes à des pièces et avoir la possibilité de fabriquer des pièces avec peu de matière et des géométries complexes. Ici, c'est encore une fois un des gros avantages de Triton Technologies, c'est qu'on peut, le fait qu'on est basé, on est sur une base de pâte enfermée dans un moule, on peut se permettre de faire des pièces en densité, comme faire des pièces très fines avec des géométries complexes. C'est vraiment aussi un des gros avantages. Ok. Est-ce que nous avons répondu à toutes les questions? Est-ce que les spectateurs ont d'autres questions à poser avant que nous mettions fin au webinaire? Donc, à savoir, pendant que si certains d'entre vous ont des questions à poser, n'hésitez pas. À savoir que donc là, nous sommes sur la fin du webinaire. Sachez que nous allons organiser dans quelques semaines un autre webinaire consacré à Triton qui répondra, qui parlera davantage de différents cas d'études sur des pièces réalisées, analyse de coûts, etc. Donc une bonne occasion de lire le webinaire à froid et de pouvoir préparer vos différentes questions sur de ROI, des exemples de pièces, etc., etc. Donc surtout, restez connectés à nos réseaux sociaux, donc chez ERM comme chez Triton, pour pouvoir assister au prochain webinaire qui aura lieu certainement dans quelques semaines. Monsieur Poirier, mon collègue, va vous répondre directement avec vos coordonnées. Monsieur Savigny, est-ce que vous pouvez nous remettre vos coordonnées? Nous allons vous envoyer tous les éléments à ce sujet, au sujet des différents coûts de la machine, du complet. Vous avez pu le voir, Triton a deux modèles de machines, une petite et une grande, on va dire. Donc, encore une fois, différents tarifs. Donc là, merci pour avoir mis vos coordonnées. On vous recontacte très rapidement. Merci, Monsieur Poirier, pour le commentaire. Mr. Poirier told us the presentation was amazing and very interesting. Donc, n'hésitez pas à rester connectés. Dans quelques semaines, on va sortir un autre webinaire, encore une fois, tous ensemble, avec des jolis cas d'études. Voilà, Rouet est en train de nous montrer des exemples de pièces avec des géométries internes très intéressantes. Encore une fois, merci à tout le monde pour avoir participé à ce webinaire. Thank you for everyone for the presentation. Thank you again so much, Triton team, sorry, for a very interesting presentation. I told to everyone to stay tuned on social network from Triton and from ERM, because in a few weeks we will hold together another webinar dedicated to parts, ROI calculation, something to go deeper on inside the technology. This will be also very interesting. And by that time, if everyone has some STL files, parts to submit to us to do some simulation in terms of costing, materials, different materials, do not hesitate to send us emails. Aurélien, my colleague, will put in commentary our email address and our website, so do not hesitate. Merci encore à tout le monde. Thank you so much, everyone, and let's.
And thank you to Yarem too. So we're happy to be here. Thank you.
Thank you so much. That's the end of the presentation. Merci tout le monde et encore une fois, à très vite pour le prochain webinaire chez RM Fabtest et Triton. Merci beaucoup. Thank you so much. Goodbye.